This is part 2 of thermochemistry notes, and we're going to be looking at heat capacity and specific heat capacity. Let's first look at some definitions. We're going to be using joules as the unit of measurement for heat. This is the SI unit of energy. We'll also routinely use kilojoules. So 1 kilojoule is the same thing as 1,000 joules. Remember, that's what the prefix kilo means. Another unit that we commonly use is the calorie. This is the amount of heat needed to raise the temperature of 1 gram of water by exactly 1 degree C or 1 Kelvin. This is related to the calories that you see on food labels. 1,000 calories is the same thing as 1 calorie with a capital C. And this is the one you see on food calories. If you have to, you can interconvert between the two. So 1 calorie is the same thing as 4.184 joules. Now, you do not need to memorize this value. I will provide it to you if you need to convert between calories and joules. Now, closely related to calories is something called specific heat capacity. And this is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree C. And the symbol for it is a capital C. The units are joules over grams times degrees Celsius. Now, typically this is just written out as joules slash grams degrees C, all on the same line. Specific heat capacity is a physical property of a substance. Let's write underneath here. This is a physical property of a substance. So, for example, water happens to have a very high specific heat capacity. In fact, it is the calorie, is the specific heat capacity. Whereas something like aluminum, you don't have to put much heat into it for it to heat up. Aluminum has a low specific heat capacity. Now we're going to end up using specific heat capacity in the equation that is shown right here, where Q equals mc delta T. Q are the units for delta H, and it's going to be measured in joules. C is your specific heat capacity, as shown right here. Delta T is your final temperature minus your initial temperature. So you'll frequently see that written as TF minus TI. Let me put that up a little higher so you can see it. TF minus TI, where the F stands for final and the I stands for initial. And then mass is going to be measured in grams. Let's try using this equation to solve some specific heat capacity problems. So here's the equation along the top here. And frequently what I find is students like to remember this by Q equals MCAT, but you have to remember that's actually delta T. Remember, Q is going to be in joules, mass is in grams, C is the specific heat capacity, there's the units, and delta T is the change in temperature. Now, you can only use this equation if the substance does not change phases, and you have to see a temperature change. So one way to look for these is you're going to see a temperature change. So let's write up at the top, look for temperature change. So you've got to see some sort of temperature change going on. Let's try this first one. We have a 500 gram sample of iron, changes from 22 degrees Celsius to 35 degrees Celsius. The specific heat of iron is known to be 0.46 joules per grams degrees Celsius. How much heat was added? So across the top here, what we're going to do is we're going to write out all the things that we need to have. So we need to have a Q, we need to have a M, we need to have a C, and we need to have a delta T. Now we know it's a specific heat capacity problem because we saw the heat change here. And then also, when you see this particular unit, you know it's a specific heat capacity problem. So we've got a 500 gram sample. Well, that would match up to a mass. And it says the temperature changes from 22 to 35 degrees C. So delta T is going to be 35 minus 22. So that's going to be 13. And it tells us we have a C of 0.46. So the only thing we're missing is Q. So let's just go ahead and write out our equation. We have Q equals 500 times 0.46 times 13. There's our delta T. And if you plug it into your calculator, then you're going to get 2990. And don't forget what your units are going to be. Since we're looking for Q, and Q is always going to be in joules, since we're using joules here also, there's your hint, then it's going to be 2,990 joules. Remember to put a box around your final answer so that I know you're done. Now, give this one a shot. If you're on track, you will get 2.7 times 10 to the 4th joules. So work the problem and make sure you get to 2.7 times 10 to the 4th joules. Note that this is almost the exact same problem, except instead of using iron, we're using water, so that the heat capacity has almost gone up by a factor of 10. So we see that it takes a great deal more heat to increase the temperature of water by 13 degrees than it does to increase the temperature of iron. Now let's try this one down here. We're going to use the exact same approach. Here we can see its temperature increased by 15.3 degrees C. So we've got a temperature change in here. It will be a Q equals MC delta T problem. So we have Q equals, M equals, C equals, and delta T equals. So Q, when 82 joules of heat, so that's our Q because the units for Q are joules. So we have 82. It's looking for what is the mass, so we don't have that one. It says our specific heat capacity, there's the units for specific heat capacity, are 0.90. And it has told us that our temperature change increased by 15.3 degrees C. So this is 15.3. So at this point, we're going to plug the whole thing in. So we're going to have 82 equals mass times 0.90 times 15.3. We need to isolate mass, and we can do that by dividing both sides by 0.90 by 15.3. So let's go ahead and do that. 0.90, 15.3. And our final answer ends up being that M equals 6.0 grams. Don't forget to put your units. Without your units, the answer is completely meaningless. All right, you try the next one. See if you can solve number 4. If you're on track, you'll get 0.129 joules per gram degree Celsius. So stop and try solving it, and then see if you get the right answer. All right, you would have gone through your list of variables and realized you were solving for C, so you would have plugged everything in, solved for C, and gotten 0.129 joules per grams degree Celsius as the specific heat capacity. We've got one last problem here. This is what I would call a very challenging problem. I'm going to give you the answer, and you can give it a shot, and then I'll go over how you actually arrive at this answer. So your final temperature, TF, equals 21.4 degrees C. Don't worry if you can't get this one. Just think of it as a fun but challenging one. Okay, 61.30, that's your joules of heat. You've got a 142 gram sample. There's the specific heat capacity. You solve for delta T and you find out that it's 1.8 degrees C. Well, you know that delta T has to equal TF minus TI, temperature final minus temperature initial. So you have 1.8 equals your final temperature minus 19.6. We got that from right there. So solving for TF, you have TF equals 21.4 degrees Celsius.